Nye, the science guy. Bill Nye, the science guy. Bill Nye, the science guy.
Hello and welcome back to my laboratory. I am physicist Ashley, and today on Inside the Lab, I'm going to be teaching you physics with my special guest, Peyton.
Dang! Man, I wish I could dunk like Capella.
You can, it's all in physics.
Really?
Yes, go suit up. Let's do this.
Okay.
Well, first, before you go outside dunking the basketball, you need to understand the physics behind dunking the basketball. Dunking a basketball is made possible because of the concept of projectile motion. A projectile is an object where the only force acting upon it is gravity. By definition, projectile motion is a predictable path traveled by an object that is influenced by the initial launch speed, launch angle, and acceleration due to gravity. So, in human words, the harder the basketball player pushes off from the floor, the more force exerts them when they go up in the air. This creates the long hang time, and the path that they travel is projectile motion. So you think you got it?
Yeah, I got it.
I'm so fresh,
If you take basketball lessons from me, you'll be dunking like a pro in no time. Now, let's look at the physics behind Peyton's dunk. According to my calculations, Peyton jumps off the ground at 50 meters per second at an angle of 90 degrees, and of course gravity is 9.8 meters per second squared. So let's calculate the maximum height that Peyton will dunk the basketball. First, we must identify our variables. So that is what I'm going to do here. So, okay, so what I have written is that Peyton's velocity is 50 meters per second. Our Vx is our horizontal component. Our Vy is our vertical component. Our angle is 90. H is height, and G is gravity, which is 9.8 meters per second squared. So our equations are these two, which is distance equals the velocity times the time plus half of the acceleration times the time squared, and that the final velocity minus the initial equals the acceleration times the time. So first we are going to find our initial velocity, our initial vertical velocity. So we're going to use this formula right here, which is saying that the velocity times the sine of theta. So we said our velocity was 50 and our angle is 90, so sine of 90. And then you're going to get your handy dandy calculator and make sure it is in degree mode since you're dealing with angles, and you're just simply going to do 50 times sine of 90 like this, and hit enter, and it gives us 50. So that's easy. So we get that our initial vertical velocity is 50 meters per second. And then second, now we can solve for time, because time equals that velocity over gravity, so 50 over 9.8. And if you stick that in your calculator, you get 5.10 when you round. And time is in seconds. And so lastly, we're going to put that all together and use that height equals times vertical velocity times time plus 1/2 the acceleration times time squared. And so that gives you 50 times 5.10 plus half of 9.8 times 5.10 squared. And when you stick all of that in your calculator, it gives you 382.449. And our unit is meters. And it is as simple as that.
Hey guys, welcome back to Inside the Lab. I'm going to show you how to cook some noodles while Ashley's getting ready for the show. So, you got to get yourself a pot about yay big. Put some water in there, you know, whatever you think's right. And then get you however many noodles you want. And, you know, just shove them in the pot. And then you got to start your fire. That's a big fart. And while you're waiting, just play on your phone and play some Flappy Bird.
Hello, it is physicist Ashley and welcome back to Inside the Lab. Today with my friend Peyton, we are going to be teaching you how to cook in the kitchen. So grab your aprons and your spatulas and let's get going. Peyton, what are you doing?
Cooking me some noodles.
It is on fire! This is not how you cook noodles!
Sorry.
We have discussed this. You can't cook! Peyton, what did you do to these noodles?
Cooking them.
Did you cook them at the right temperature?
What's temperature?
Oh boy. Well, this brings us to our lesson in physics today. Today we are going to be discussing heat. So the first thing we're going to do to fix these noodles is dump out the bad noodles and put new water in the pot. Okay, so we're going to put the pot on the stove and then we're going to turn it up to some medium heat and we're going to let that boil. Okay, so right now our water is boiling so that we will be able to cook our noodles, and they are cooking at a temperature that is going to eventually heat up to 212 degrees Fahrenheit, which is the degrees at which water boils. And temperature is the intensity of heat in an object, and there's 3 scales of temperature: Celsius, Kelvin, and Fahrenheit. And today we are cooking with Fahrenheit. And as our noodles cook, we can see, come look, that the water is boiling. So it is getting closer because the water, the little bubbles are coming up, and that process is called convection, which is the heat going through the liquid as it rises from the bottom of the pan to the top. So we are almost ready to cook our noodles. Okay, Patin, can you see that the water is boiling? That means it is time to stick in our noodles. So get yourself a handful of noodles out of the box, and you are going to break them in half, like so, and stick them in, and be careful because the pan is super hot. And then you're going to take a little ladle like this, and you can use that to mix up your noodles so that they will cook a little bit faster. So you are just going to let them sit like that until they get nice and soft, and then you will be able to eat your noodles. Okay, so we've been talking a lot about terms with heat and temperature and stuff like that, and you may be asking yourself, Physicist Ashley, how does this apply in math? Well, I'm fixing to show you, so let's look at an example. The question says, How much heat is needed to warm 1 kilogram of cold water from 10 degrees Celsius to 65 degrees Celsius if specific heat is 4,180 joules per kilogram Celsius? So, this is one of the simpler heat workout problems. So we're going to use the equation MCAT, which says Q equals M times C times change in temperature. So, M is our mass, which is 1 kilogram. It's always good to write out your variables. And then C is the specific heat, which is 4,180, like it tells us over here, joules per kilogram Celsius. And the change in temperature, we read in the problem, it said it goes from 10 degrees Celsius to 65, so we're going to do 65 minus 10, which is obviously 55. And then we're going to plug that onto our equation. So it is asking for heat, which is Q. We're going to plug in our mass, which is 1 kilogram. Our specific heat, which is 4,180. And our change in temperature, which is 55. And then we're going to stick all of that in our handy dandy calculator. So 1 times 4,180 times 55 and hit enter, and there you go. So it gives you a big number, and it's just easier if you put it in scientific mode. So when you do that, you get 2.3 times 10 to the 5th joules. And there you go. Okay, so our noodles are clearly cooked now. We can see the process of convection happening in the pot. The bubbles are rising and sinking back to the bottom, so it's clearly boiled and our noodles are ready. So we're going to go ahead and turn off the stove and let them simmer. And then you're going to take a strainer, which is over here. And you're going to take this to the sink and dump the water out of the noodles. Okay, so then you're going to dump it out like this, and be careful because the water is super hot. And then it is best to just rinse off your noodles to kind of cool them down. We're going to set that right here. Then we're going to rinse out our pan. And this process is thermal equilibrium, when two different objects reach the same temperature. So the cool water becomes hot from the hot pan, and the hot pan becomes cool from the cold water. Let's call Peyton and see if she's ready to try these delicious noodles. Peyton! So what do you think?
Wow, you can cook and do physics?
Inside the Lab. I am physicist Ashley, and today on the show we're going to discuss. Whoa! Peyton! What is wrong with your face?
What do you mean?
What mirror did you use when you got dressed this morning?
My car side mirror. I was in here.
Oh no. Well, this brings us to our lesson in physics today. Today we are going to be discussing mirrors. So what you need to know is there are 3 types of mirrors: plane, concave, and convex. The plane mirror is a flat surface, and an example of this would just be like a regular day-to-day mirror. A concave mirror is inwardly curved, so it magnifies, for example, a makeup mirror, which you should have used. And lastly, a convex mirror curves outward and creates a large field of view. For example, a safety mirror in your side mirror on your car, which is what you should not use to do your makeup.
Okay, so I should use concave mirror.
See, you're learning already. Now, while our friend Peyton here goes and fixes her face, we are going to see how this math will apply in physics. Okay, while Peyton is fixing her makeup, let's do some math. So here's an example problem involving meters. A convex security mirror has a radius of curvature